In this video, I will show you the derivation of efficiency of full wave rectifier circuit. While deriving the efficiency of full wave rectifier circuit, on the way I will calculate IDC, the amount of DC current that presents in the output or load current. I will calculate VDC, the amount of DC component presents at the output voltage. I will calculate the RMS, the RMS value of the AC component that presents in the load current. I will calculate VRMS, the RMS value of the AC component that presents in the output voltage. In a full wave rectifier circuit, we apply a pure sinusoidal voltage. So this is our input voltage VI. So if I write down the equation of VI, I will get VI equal to Vm sin omega t. In the output of a rectifier, we get an unidirectional or rectified voltage or a pulsating voltage which contains both AC and DC component. Therefore, our load current will also contain AC and DC component. See, from 0 to 5 interval, VO equal to Vm sin omega t for omega t interval phi to 0. Now look at the phi to twice phi interval. You will see it will follow the same equation, Vm sin omega t for omega t equal to twice phi to phi. Now look at the load current. Our load current is a unidirectional current, so our load current IL will be equal to Im sin omega t for interval 0 to phi. See, from phi to twice phi, it will be Im sin omega t. Here I will calculate the efficiency of a full wave rectifier. Which we will denote as eta, but I will calculate percentage of efficiency. So I will take eta equal to, we calculate the efficiency by taking the ratio of output by input and multiply that with 100. So here we will get DC power output, and we will apply AC power input, and we will multiply this with 100%. In the equational form, I can write it like this: DC power is output DC power, so PODC, and input power will be PIAC. We will multiply that with 100. This is how we calculate the efficiency of a full wave rectifier. And we calculate the PODC in a full wave rectifier by using this formula, IDC square into RL, and PIAC by using this formula, I RMS square into R2 plus RF plus RL. If you look at the structure of a full wave rectifier circuit, you will see the secondary winding has a resistance of R2. The diodes has forward resistance or dynamic resistance or AC resistance RF, and the load resistor RL. Therefore, I will get our PIAC equal to IRMS square into R2 secondary winding resistance plus dynamic resistance of the diode plus the load resistor RL. Another thing is that what will be the value of Im? What is this Im? See, Im is the maximum current at the load, and it will occur when the Vm will be at its maximum value. We calculate Im in the circuit by using this formula. Im equal to Vm divided by the secondary winding resistance R2 plus diode forward resistance Rf and the load resistor RL. If we ignore the value of R2 and Rf, I will get Vm equal to Im into RL. Now see, to calculate PODC or output DC power, we have to calculate the AC. We have to calculate the DC component of the output or load current, and we have to calculate the RMS value of the AC component in the output current. Now I will show you how to calculate the DC or average value of the load current and load voltage. See, this is our load current. This load current contains both AC and DC component. Similarly, the output voltage will also contain the DC and AC components. Now see, I will calculate the DC or average value of this output current or load current and load voltage. To calculate the DC value of any waveform, we use this formula, area under the waveform over full cycle. Here I will calculate this DC value for the load current. So area under the load current over full cycle divided by the period of the cycle will give us the DC value of this output or load current. That means I have to take the area of this full cycle from 0 to 5 interval for this load current. To calculate that area, I will take the integration of our load current IL over full cycle 0 to 5 I m sin omega t with respect to d of omega t. Here we will integrate this with respect to omega t, because in x-axis we are taking the omega t and this phi will indicate the amount of omega t, and period of this cycle will be 0 to 5, because after 5 you will see the same thing will be repeating in the upcoming cycles. Therefore I will get integration of 0 to 5 I m sin omega t d omega t divided by phi. Now if I take the I m out of the integration sign, I will get I m divided by phi, integration of 0 to 5 sin omega t d of omega t. If I integrate the sin omega t, I will get minus cos omega t. So I will get I m divided by phi minus cos omega t with upper limit phi and lower limit 0. If I put the value of phi and 0 in place of omega t, I will get I m divided by phi minus cos phi minus cos 0. So I will get I m divided by phi into 1 plus 1, from which I can calculate IDC will be equal to 2 IM by phi. This will be our DC current or the DC component of load current. IDC equal to 2 IM divided by phi. Now what will be the output DC voltage? VDC will be equal to IDC into RL. Here IDC is equal to 2 IM by phi into RL. See, IM into RL will represent the maximum value of the voltage. So I will get 2 Vm divided by phi. In case of a half wave rectifier, I have shown you that our IDC will be equal to IM divided by phi, and our VDC will be equal to Vm by phi. So in case of full wave rectifier, you will see the value of IDC and VDC will be 2 times of the IDC and VDC in case of half wave rectifier circuit, because in case of half wave rectifier we will get the output only in one half cycle. Therefore the IDC and VDC in case of full wave rectifier will be twice of the half wave rectifier circuit. Now here we have to calculate the PODC. PODC equal to IDC square into RL. So if I take the square of this IDC, I will get 4Im square divided by phi square and multiply this with RL. Now I will show you how to calculate the RMS value of the load current and the RMS value of load voltage. Previously I have told you that the output voltage will contain both AC and DC component, and the load current will also contain AC and DC component. The RMS value of load current indicates the RMS value of the AC component in the load current or output voltage. So to calculate the RMS value of any waveform, see this word is RMS, root mean square. At first, let's say I will calculate the RMS value of the load current. At first I will take the square of the load current IL, so it will be IL square. After that I will take the average of this IL square. To calculate the average of this IL square, at first I have to integrate this IL square from 0 to the period t and divide this with the period t. So this will be mean of the square. After that, if I take the root over of the mean of square, I will take the average value. Therefore we calculate the average value of any waveform by using this formula. Area of the square of load current over full cycle divided by the period of the squared waveform, and I will take the root over of this whole thing. See, if I take the square of the load current, I will get an waveform like this. This is IL, and IL is equal to Im sine omega t, and all the values of the load current are positive. If I take the square of this waveform, I will get Im square. That means from 0 to phi I will get Im square, phi to twice phi Im square, twice phi to 3 phi Im square. So it will be our IL square, and value of IL square will be equal to Im square sine square omega t. Okay, and you will see the period of this IL square will be equal to phi, because after phi you will get the same repetitive things. So I will calculate the RMS value by using this formula. Period of the square waveform is equal to phi, and area of under the square of load current over full cycle. See, this is our full cycle. I have to calculate the area over this 0 to phi interval, and here the equation of this IL square equal to Im square sine omega t. So I will calculate the area by integrating this within 0 to phi interval. 0 to phi Im square sine square omega t d omega t. We will integrate it with respect to d omega t. Now we know that we cannot integrate sine square omega t. We know another form of sine square omega t. let's say if I have 2 sin square theta, I can write it like this: 1 minus cos 2 theta. Now to get 2 sin square omega t here, at first I have to take a half in the outside of the integration sign and multiply this with 2. So I will get root over 2 phi I m square integration of 0 to phi sin square 2 sin square omega t with respect to d omega t. So here I will get I m square divided by twice phi integration of 0 to phi 1 minus cos 2 omega t, and we will integrate it with respect to omega t. Now if I integrate it, I will get root over I m square by twice phi omega t minus sine 2 omega t divided by 2 integration limit 0 to phi. Now if I put the value of phi and 0 in place of omega t, I will get I m square twice phi minus sine 2 phi divided by 2 minus 0 minus sine 2 into 0, so plus divided by 2. From here I will get only the sine twice phi, it will have a value of 0, this will have a value of 0. In the exponential I will take the half because root over indicates 1 by 2. So here I will take I m square divided by twice phi into phi because all other terms will be 0. So here you will see our I RMS will be equal to I m divided by root 2. It will be I RMS. Now what will be the value of VRMS here? You will see VRMS will be equal to IRMS into RL. Here IRMS is equal to IM divided by root 2 and multiply this with RL. See, IM into RL will represent the value of VM. So I can write VRMS will be equal to VM divided by root 2. See, from here I can write our input AC power PIAC will be equal to IRMS square into secondary winding resistance plus forward resistance of the diode plus the load resistor RL. Now IRMS indicates IM divided by root 2. So here I will get IM square divided by 2, multiply this with R2 plus RF plus RL. Secondary winding resistance R2 and the forward resistance of the diode are very small. Therefore I can say that R2 plus RF which will be much smaller than the value of load resistor. So I can neglect the sum of R2 and RF. Instead of that I will take only RL, IM square RL divided by 2. Now we will calculate the percentage of efficiency. Percentage of efficiency eta equal to DC power output PODC divided by PIAC into 100 percent. See here, our PI is equal to IM square RL by 2. And see, POD is equal to 4 IM square divided by phi square into RL. 4 IM square phi square into RL. This RL will get cancelled with this RL, and this IM square will get cancelled with this IM square. These two will get multiplied with this 4. So in the numerator I will get 8, and in the denominator I will get phi square into 100%. From here I can calculate percentage of efficiency will be equal to 81.06%. See, the maximum theoretical efficiency for the full wave rectifier is equal to 81.06%, and you will see efficiency of full wave rectifier is exactly double or twice of the efficiency of half wave rectifier. As full wave rectifier has the highest number of efficiency for the rectification, we will use full wave rectifier instead of half wave rectifier. Okay, that's it. Thank you.